Okay, so in the last class we gave an introduction to what is called stochastic process. There is earlier we used to consider random variables, that is you have an experiment and depending on the outcome of the experiment the variable takes a value. Since outcomes are random, the variable takes values in a random way and we call it random variable. So, we studied single random variable, we studied double random variable and functions of random variable and all that, they are probability densities and probability distribution functions. In the case of process, it was extended to functions, that is depending on a particular experiment, you got just a function. Function could be continuous, function could be discrete, but a function discrete in time, a function emerges and that function is then random because depending on depending on the particular outcome at hand, you get just one function, right. So, that set of all functions, this is called the process. Okay. This phenomenon is called the process. The set of all possible such random functions is called the ensemble. Okay. You can just stick to a particular time point, maybe t or t1 say on the time axis. So, at that point every time you have the experimental outcome you get one value because the function takes a particular value, next time the value changes. So, the value the value that this function takes, if you call the function x of t, then x of t1 for a fixed t1 itself is a random variable and that is true for all such t1s on the time axis. So, basically a random process is nothing but an infinite collection of random variables which take different values depending on the experimental outcome at hand. Okay. So, it basically is random functions. Then in the last class we also discussed the meaning of joint probability density, joint probability distribution functions given a stochastic process or random process, okay, and then correlation, covariance, okay, and related things also are defined. Today we will be considering a particular class of random process called stationary process, which are very important. You see, very general random processes are fine theoretically, but for practical purposes they are very difficult to be made use of. So, we need to enforce some additional assumptions on a random process, so that their statistical properties or statistical characteristics, they become more simpler for handling in practice. Stationary process is one such notion actually. Suppose you are conducting an experiment and depending on the experimental outcome you are observing some waveforms. So, waveforms are random, okay. Every time you get a random waveform, okay, and this whole phenomenon is called the random process. So, maybe you have something like this, okay, and you fix a time point t1. So, this time you find, if you call the random process xt, this is the time axis. So, these are functions of time, also I have taken continuous functions of time. So, at t1 you get some value this time, okay, and maybe at t2 you get some value, but next time when you observe the same waveform, maybe at t1 you get only this much and here you get negative. Next time maybe at t2 you get very high value and like that, okay. This is possible. Now, in the case of stationary process, we assume that this randomness, what is randomness? That this tendency of this waveform to fluctuate around this time axis, this randomness, that okay, this time you got one waveform, next time the waveform thoroughly changes, next time it changes again. So, this tendency to fluctuate from experiment to experiment, fluctuate around this axis, this is not having any bias over some zones of the time axis. This randomness is rather homogeneously distributed on the t axis. This means that at point t1, whatever be the statistics you have for the random variable x of t1, same statistics should hold at another time point, say t2. Okay. That is, as we move along the time axis to the right or to the left, the randomness, the properties, the randomness properties of this process, they do not change. For a particular waveform, it may so happen that you get a high value here and a low value here, next time the value changes and all that. But when you talk in terms of the statistics, like say probability density or probability distribution functions, okay, then whatever you have at one time point, the same thing you should have another time point. And that is true for all the time points on this axis. Then this process is called strict sense stationary. Not only stationary, strict sense stationary. This is the ideal stationary situation, that the statistics does not change, statistics of the random variables x of t for a particular t, it does not change if you move t from minus infinity to infinity. At all points the statistics remain same. Okay. So, the for that matter say probability density of this random variable x of t1 at t1, okay, because that is a random variable, it has its own probability density. You should have the same value, same thing at t2, at t3. That is that randomness. Please try to visualize this way. The randomness, it does not really look at this time axis. It is just, randomness is just homogeneously distributed, okay, along this time axis. It is not biased, that okay, it is not biased on some sectors of the time axis. That is, it is not that okay, around t equal to 0 maybe in a zone, it has got some kind of property, and as you move further down from the origin, maybe another sector on the time axis, maybe here you have got some other kind of statistical properties. No. Okay. The statistical properties do not change over. This is a very qualitative statement. I will quantify it. I will use the notions of probability density, probability distribution functions, okay, to really give a proper definition of this. But I am just trying to say that randomness for this process, okay, is really uniform along this axis. This process is as much random, if I may put it this, as much random say at origin as it is at t1, as it is t2. This randomness property as given by the statistics, that is the probability densities, is same whether you are seeing it at origin or at point t1 or t2 or any other point. Then it is called strict sense stationary process or SSS. This means that suppose x of t corresponds to a random process. That means there is an experiment. Every time you observe a waveform, you get some waveform. Every time you observe, have an outcome, experimental outcome, you find some observation, some waveform xt. Waveforms are random. A particular xt is a sample function. Okay, this is just repetitions of what we already have discussed, and collection of all possible xt's is called the ensemble for this random process. Okay. Now, this means the stationarity means that suppose you are considering the statistics means either probability density or distribution, maybe we stick to probability density, say at a particular time, say t1. What does it mean? That this waveform x of t, if you observe it at time point t equal to t1, then you have got a random variable x of t1. It is the probability density of that random variable. So, that random variable lying between x and x plus dx is given by this density times dx. Okay. Now, if it is that is a general definition, but if it is stationary, then whether you observe this probability density at time point t1, that is for the random variable x of t1, or at some other time point t2, that is for the random variable x of t2, you should get the same thing if it is strict and stationary. That is, it should be same as px comma t2 and so on and so forth. You can take px comma t3, px comma t4 and like that, you should have the same thing. Okay, this for individual densities. This means px comma t independent of t. That is, if the random process xt is given and you find out for a particular, for any point t, the random variable x of t, if you look at its probability density, that should be independent of the t that you have chosen. Okay. But these are only individual densities. But you see, this does not define the, this does not give the entire statistics. We have to consider all joint densities. Okay. Individual densities are just individual densities. It does not give us any, idea about the joint variation. Okay. But when it is strictly stationary, it's not only the individual statistics is independent. Okay. Of time, that is, you observe the same thing at various time points, but this joint statistics also should be time invariant. That means, for that matter, suppose you have got now P x1, x2, semicolon, t1, t2. What does it mean? Actually, that there was a random process x of t. You are fixing two particular time points t1 and t2. At t1, you have got the random variable x of t1. At t2, you have got the random variable x of t2. What is the joint probability density of x of t1 and x of t2? That is given by this. So, the joint probability of x of t1 lying between x1 and x1 plus dx1, and at the same time x of t2 lying between x2 and x2 plus dx2, that is given by this function times dx1 dx2. I am not writing all this because this is by now pretty well known to all of you, okay, because this is just the definition of joint density. So, I repeat again, x of t1 and x of t2 are two random variables. This is a joint density. It means the joint probability of x of t1 lying between this x1 and x1 plus dx1, and at the same time x of t2 lying between x2 and x2 plus dx2. That is given by this density function times dx1 dx2. That is the meaning of this joint density. But if it is strictly stationary, then what should happen? That okay, I fix up to two time points t1 and t2, okay, and based on that I am getting this probability density. If it is strictly stationary, it should not, I should get the same thing if instead of t1 I say t1 plus some constant c, and instead of t2, t2 plus c. That is, whether I choose two time points t1 and t2, that is, I am drawing a figure here, this is the time axis, whether I choose t1 and t2 here and see the joint statistics of the two random variables x of t1 and x of t2, or I see the same thing at two other points t1 plus some constant c, t2 plus some constant c, just delay both the points by the same amount, that is important. That is joint density between two variables which are situated at a gap of t2 minus t1. So, whether you see them at t1 and t2, that is, if you call it t2 minus t1 is equal to suppose tau. So, actually it amounts to saying that joint density of two random variables which are situated at a gap of tau. So, whether you see them at t1 and t2 or at t1 plus c and t2 plus c, as long as the gap remains same, you should see the same density. Okay. This is in the case of joint statistics involving two variables. That means this should be equal to just p x1 x2, this will be semicolon, and neither t1 nor t2, you can say tau, where tau is equal to t2 minus t1. So, it should depend on neither t1 nor t2, but this density would depend only on the gap between the two. But again, this is only joint statistics involving two variables. Strict stationarity applies to joint densities involving any countable number of variables, x1, x2, x1, x2, x3, x1, x2, x3, x4, so on and so forth. So, in general, from this you can now generalize the thing that if it is strict sense stationary, maybe I write out here strict, because I did not write anywhere, strict sense called S. Okay. So, in general, if you have x1, x2 dot 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 up to x p colon t1, t2 dot 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 tp, what does it mean? Very simple, x of t was the random process. So, you are fixing some time points t1, t2, tp. X of t1 is a random variable, x of t2 is a random variable, dot dot dot, x of tp is a random variable. It is a joint density of them. So, that the joint probability of x of t1 lying between x1 and x1 plus dx1, similarly x2 lying between x2 and x2 plus dx2, dot dot dot, xp lying between xtp lying between xp and xp plus dxp, that is given by this density function multiplied by dx1, dx2 dot 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 dxp. Okay. So, again here it should not matter if I advance the points, all the points, if I just shift instead of t1 I call it t1 plus c, delay it or advance it, that is move it rightward, move the function x of t rightward or backward. That is, instead of observing this joint density between variables which are located at t1, t2 dot dot tp, if I give a constant shift to all of them, that is maybe t1 plus c, t2 plus c dot 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 tp plus c, I should have the same thing. Okay. That means it should neither depend on T1 or T2 or say T3 dot 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 Tp. It depends only on the gap between T2 to T1 and T3 to T1 and likewise. Okay. Because that gap remains invariant. If you give the same shift C to T1, if you add the same C to T1, T2, T3, maybe put a T3 here, dot dot dot. Okay. Is T3. Okay. If you give the same, if you add the same constant C, you get defined time points T1 plus C, T2 plus C, T3 plus C, dot 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 dot. But strict sense stationarity implies that you should get the same density function. So, this only means that what is important is not the absolute positions of T1, T2, T3, etc., but only the gap, the difference between T2 to T1 and T3 to T2 and T4 to T3. Okay, that is what is important, because that remains invariant whether you have T1 plus C and T2 plus C or T1 and T2, or similarly whether you have T2 T3 or T2 plus C, T3 plus C. Okay. So, that means under strict set stationarity this becomes a function of T2 minus T1, if you call it tau 1, then T3 minus T2 dot 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 dot, in general Tp minus the last but one Tp minus 1 variable less. Earlier it was p variables, but the gaps result in p minus 1 variables. You can call it tau 1, tau 2 dot 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 tau p minus 1. Okay. Then we can even generalize this concept. Maybe there are two random processes x of t and y of t, and they are jointly related. So, I can define strict state stationarity for joint processes, that is jointly strict state stationary, jointly SSS, x of t and y of t. This also means that if you are looking for now joint density between x and y, maybe you just start with one variable only. It is easily generalizable. So, I will take one. Suppose it is given is joint density x1 y1 colon t1 prime prime terms apply to y and non-prime quantities apply to x. Okay. What does it mean? It means this is a joint density, so that x of T1 probability, joint probability of x of T1 lying between x1 and x1 plus dx1, and then at the same time y1 lying between y T1 prime lying between y1 and y1 plus dy1 is nothing but this density multiplied by dx1 dy1. Okay. Since this is a pretty standard stuff by now, because we have been dealing with this definition of probability density, joint and single, I am not writing them. Okay. Now, if it is jointly strictly stationary, it should depend only on the gap, that is this way semicolon. You should have the same thing if you advance them by some constant, which means it depends only on the gap between the two, difference between T1 prime and T1, not the absolute values of T1 prime and T1. Okay. Similarly, if you have x1, x2, y1, y2 and T1, T2, T1 prime, T2 prime, you can define like that. Okay. All right, it is a very simple generalization. And just for definition's sake, if you have got a process Z(t), which is a complex process, Z2 will be strictly stationary if, maybe if and only if xt, yt both are SS and jointly SS. Individually they are stationary process and they are also jointly stationary, both in the strict sense. Okay. This strict stationarity, it is more theoretical in the sense that it is an absolute notion of stationarity, and that is why you talk in terms of the absolute statistics, that is probability density. As you know, probability densities define everything. If you know all the probability densities, individual and all joint densities of the process, then the entire statistic of the process is characterized. So, if when I define stationary strict stationarity in terms of this or when I define stationarity in terms of this statistics remaining invariant on the choice of time points, then this is really an absolute notion. But for practical purposes, this is not so good really. We can take a special case of this strict sense stationarity, which is called wide sense stationary, WSS, which is really very, very useful for all practical purposes, especially in communication, control, signal processing and others, estimation, detection and all. This is called wide sense stationary, where we go only up to second order and talk in terms of correlation and mean, not in terms of probability density. Okay. So, I will come to that now. Also called WSS. In wide sense stationary, I say that we will be considering only moments, but moments only up to second order. That is, first order moment means mean and second order moment is correlation. And there we will be enforcing some notion of stationarity, and that is all. And with that only we will remain happy, and those processes which satisfy them will be called by us as WSS processes, wide sense stationary processes. So, here when it comes to the first order moment, we say that given a random process x of t, if you take for a particular time t the random variable x of t, and if you take its mean, that mean should be invariant, mean should not depend on t. That is, whether you observe the mean at a particular point t1 or at t2 or t3, you should get the same thing, and then you can call it just mu. It does not depend on t. See, I tell you, for a particular waveform, it may so happen that you can get a very high value at T1 and very low value at T2, but next time it can change. If it is stationary, maybe at T1 you get very low value and T2 is high value. So, when you average out, you get the same mean at both T1 and T2. This happens if the randomness does not have any bias on the time axis. It is not that it gives high valued high values to the process at T1 and very low range of values to the process at T2. Okay, it's not blind, it's just very fair, it's just homogeneously or uniformly distributed. The randomness I am talking, I am not talking probability, it is the randomness, the fluctuating tendency or this inner properties of fluctuate, that is just uniformly distributed along the time axis. So, at any point you get the mean, at some other point also you get the same mean. That is for first order thing. In the case of second order thing, we know the correlation, and I am considering the complex valued processes to be more general. So, there we know what is the definition of correlation, xt minus tau suppose. This correlation, this should also depend not on what is t and what is t minus tau, but only on the gap between those two samples. That is the degree to which two samples are correlated in the random process. That should not depend on what their absolute locations are, but how far they are separated. So, their gap. So, whether you are observing two samples, like whether you are observing two samples here and here or observing them here and here, as long as the gap is same, these two gaps are same, you should get the same correlation. You can call autocorrelation. So, the absolute time points, these 2 points or these points, they do not matter, because again this randomness is uniformly distributed along this axis. So, the property of correlation, the correlation characteristics of this process, that is how to what extent two samples are correlated, that characteristics, that does not change whether you are between 2 points here or whether you are seeing it between 2 points here, as long as that gap between the two remains unchanged. This means that then this should be a function of only gap tau. You can also, in some cases I can put Rxx, especially when two random processes are involved, xt and yt. Then Rxx means actually you are taking the correlation between x and x. So, Rxx, that is autocorrelation. If it is x and y, Rxy, like that. But loosely, especially when I do not have any other process involved, I will drop this subscript for the sake of simplicity, and it will become just R of tau. Okay. What is R of 0? We know it is nothing but E of xt minus tau, that is 0 star. So, there is xt into xt star, that is mod of xt square, which is nothing but the average power. Average, that is for any instant you are taking the mod square, so the instantaneous power, and they are averaging. Because of stationarity you get a constant value independent of t, and that is the average power, and obviously this is greater than or equal to 0, power can never be negative. Okay. Just to give an example, suppose x of t is a WSS process. And is given that therefore, its autocorrelation R tau is some constant a times e to the power minus alpha, say mod tau. One thing I forgot to mention, that R tau, maybe I mentioned here another property I forgot to mention. I will come back to the example soon. R tau, which is same as E of x t x star. This is a very important property. I mean, I just forgot to mention. This is same as, my claim is R conjugate minus tau. Why? If you take R conjugate, I am working out here and then I will erase it. What is R star tau by this definition? Conjugate applied inside, so it becomes E of x star tau, and this becomes x t minus tau, and then you are making minus tau. So, minus tau means it becomes t plus tau. Okay. T plus tau you can call as maybe T1. So, T becomes T1 minus tau. So, this is nothing but E of x T1 into x star T1 minus tau, which is nothing but autocorrelation at a gap of tau. So, this is nothing but R tau. So, that proves it. Okay, that proves it. So, in the case of complex valued processes, autocorrelation sequence actually is a Hermitian sequence. That is, if you take the negative of the lag, tau is called the lag, LAG lag, negative of the lag, and then put a star here, then R star minus tau becomes same as R of tau. In the case of real valued process, the conjugate has no meaning. So, it is just an even function, R tau and R minus tau, they are same. Okay. Now, I first erase this part. Okay. Now, this is just as an example, x t is a WSS process, its R tau is given, I do not know its mean though. Okay. You can assume 0 mean, mean will not be of any use in this example. R tau, as you can see, it is e to the power minus alpha mod tau. This mod tau is important. Mod tau makes it sure, make sure that R of tau or R of minus tau they are same, because it is only mod of tau, that is important. And if this is given, then this example says that suppose you have to find out x of 8, there is a t equal to 8 minus x of 5, this difference, just for some reason you want to find out the expected value of this difference. How much will that be? When you square it up, you get E of x square 8, but x square 8 expected value of that should not depend on the time, whether it is 8 or whether it is 4 or 5 or okay. It is x square t. So, basically R 0. I repeat again, first term is E of x square 8, there is x 8 into x 8, there is correlation with lag 0, whether it is 8 or 80 or 800 does not matter, x 8, x square 8 means x of 8 into x of 8. So, 2 samples with lag 0. So, expected value of that product is nothing but correlation of lag 0. Similarly, there will be an x square 5 term that will give rise to another R 0 minus twice E of x 8 x 5. So, there is a correlation term between 2 samples, one is at 8, another 5, lag is 3. So, that will give rise to twice R 3, and now you know R 0 is how much? A, e to the power minus alpha 0 is 1. So, R 0 and R 0, so twice A minus twice A into e to the power minus 3 alpha, tau is 3. This is just an example. Okay. This was correlation, and there is an equally important concept called covariance. Okay. Covariance C, so T1 T2, it means E of minus the mu at T1, this is a general definition, x of T2 minus mu T2 star. Now, if you expand it, and we know it is essentially what kind of process? It is a WSS. So, this cross term will give rise to what? E of x T1 x star T2. So, lag is T1 minus T2, so that will give rise to R T1 minus T2. Then mu T1 which is a constant, expected value of x T2 star, which is same as conjugate of expected value of x T2, but expected value of x T2 is the mean at T2, but since it is WSS, mean at T2 or mean at T1, they are all same, mu T1, mu T2, they are all same. You can just call them mu. Okay. So, this is mu into, maybe for your sake I write like this, another cross term, again mu star and then these are constants, the last one. So, no expectation operator, mu and mu star. This only means what is E of x T2, that is mu independent of T2 or independent of T1, okay, independent of T, because it is WSS. So, you get another mu star, mu star. Similarly, E of x T1, you still get mu, not mu of T1 or not mu of T2, because it is independent of the time T. So, mu. So, again another mu star mu or mu star and a mu star with a positive sign. So, effectively you get R of okay. Then there is some definition of correlation, covariance correlation coefficient. Correlation coefficient, maybe you can call the R tau, is nothing but the correlation. So, you understand one thing, that correlation, there is a covariance also is a function of, then for a WSS process, the covariance also is a function of the lag, the gap between the two time points chosen, T1 and T2. It is not a function of T1 and T2, it is a function of T1 minus T2, that is tau. So, in this case, the definition is, original definition of correlation coefficient is C of T1 comma T2, there is a covariance between T1 and T2, the two samples are T1 and T2, divided by square root of C T1 comma T1 into C T2 comma T2. But C of T1 comma T1 or C of T2 comma T2, they are now same, because they amount to the same thing, because it is a function of the lag. T1 and T1 lag is 0, T2 and T2 lag is 0. So, square and square root, so they cancel. So, you get basically C of lag 0. This is a correlation coefficient. Okay. A particular case where C tau, the covariance C tau is some constant n times delta tau, where delta tau is the impulse function, unit impulse function, or also called Dirac delta function. Then this is called White random process. Why white? Some of you already may know, but we will discuss all this when you consider power, spectral density and all later. Okay. What does n into delta tau means? That this covariance. What does covariance mean actually? It really, there is a mean mu here, there is a mean mu, okay, between two random variables. Suppose you are taking two random variables at t1 at t2, the gap is tau. This is mean mu. Sometimes it is taking value above this, and maybe this is here. Covariance means you take only the difference, that is the deviation across the mean between the two, multiply and add, multiply and average. Now, if these two variables are really not having any correlation between them, if they are very much independent, then sometimes this difference can be positive, but this can be negative. This difference can be negative. Sometimes this difference can be negative, this can be positive. Sometimes both positive, sometimes both negative. Okay, because there is no relation between them. They are independent. They are sort of free of each other. In that case, if you average out the product, you should get 0. So if this C tau 0 implies uncorrelated samples. Now, for this white random process, C tau is given to be n into delta tau. We know that delta tau is 0 at all points except at t equal to 0, at all points it is 0. So, for any non-zero lag, C tau is 0 for a white process. That is, if you really take a white random process, take any two samples which are not located at the same time point, then they are uncorrelated, because covariance is 0. Okay. This is the meaning of white random process. I give an exercise for you, we will take it up in the next class. Suppose it is given that xt is a WSS process, and you define one random variable s by integrating, that is, every time you observe an xt, you integrate it within a range minus t to t. Obviously, whatever you get, that also is a random quantity, because it changes from experiment to experiment. S is a random variable. Okay. If you want to find out, and also you can assume that it is a zero mean process. Zero mean. Zero mean means E of xt, which is independent of t, some constant, that constant is 0. So, you have to find out the variance of S, which is nothing but E of S minus its mean whole square. I am not taking any mod, because everything is real. Xt is a real value process here. Mean is 0. What is the expected value of S? What is E of S? That is E of this integral. E is a linear operator, integral is a linear operator. So, you can take E inside the integral, and E of xt is given to be 0. So, E of S is also 0. So, what is the variance of S? S minus 0, S minus S, mean square, mean is 0. So, E of S square. Now, given S and given xt to be the WSS process with some covariance function or correlation function, autocovariance or autocorrelation function, what is E of S square? But that means S into S. So, you integrate twice, minus t to t, minus t to t. Once you have got maybe a variable x t1, okay, dt1, that will give you S, again x t2 dt2, that also will give you S. So, dt1 dt2, and again as I said, integrals are linear operators. So, you can bring the, and expectation also is a linear operator. So, they can be interchanged. So, you can bring E directly over this product x of t1 into x of t2. I erase this part. So, this gives rise to if you integrate, if you apply the E on these, then what you get is R you can call it C also, because it is a zero mean process. So, for zero mean process, autocorrelation and autocovariance or correlation covariance remain same, because mean is 0. This integral dt1 dt2 up to this is fine, but this since this is a function of neither t1 or not t2, but this is a function of only the gap. It is a function of neither t1 nor t2. T1 and t2 they are varying, but whenever t1 and t2 their difference is constant, you get the same value. T1 is going from minus T2 plus T, T2 is going from minus T2 plus T. So, there is a box, there is a square around the origin, okay. One side, I mean going from like a square like this, minus T minus T2 plus T, again plus T minus T. The integral is done within this, but on those points where T1 minus T2 is constant, on those lines, those points, this value remains same, because this is a function of neither T1 nor T2, but it is a gap, it is a function of the gap. So, you can identify those points, and since on those points R is constant, you can take out R as constant and carry out the integral by moving those points, across this entire square. Actually, I am trying to give you hint, but by following this kind of procedure, so that this gives rise to, this integral can be written as a single integral. This I will not do today. It is 2t minus mod tau and R tau d tau. Because R is a function of tau really, it is not a function of T1 or T2, it is a function of the gap. So, that this double integral can be written like this. Okay. You can also see that it automatically follows xt also is WSS, but reverse is not true in general. Okay, in general reverse is not true. Why? How this follows, that if xt is fixed and stationary, it is also White's and stationary. Obviously, if it is fixed and stationary, and now you want to find out the correlation between 2 points, xt1 and xt2, obviously we will be multiplying it by the joint density T1 T2 dx1 dx2, right. This will give you the correlation or T1 comma T2. And what is R? T1 plus C, T2 plus C, you can just replace x of t1 plus c, t2 plus c. Now, since it is fixed and stationary, p of x1 comma x2 and t1 plus c, t2 plus c same as p of x1 x2 t1 t2. Okay. And it does not matter whether it is x of t1 or t1 plus c, t2 plus c, because these variables are I am taking over the entire range minus infinity to infinity, minus infinity to infinity. So, you will get the same thing. So, this will be equal to this. Are you following this? Okay. What I am saying is this: if you move t1 to t1 plus c, t2 to t plus c, probability density still remains same. Okay. We get the same density function, and x of whether it is x of t1 plus c and x of t2 plus c or x of t1 and x of t2 does not matter, because this is the variable of integration. In fact, instead of calling it x of t1 and x of t2, I should rather change them to this. Okay. So, obviously, these two are same. Same applies for the mean easily. Okay. But you can easily see the reverse is not true in general. Okay. Reverse is not true in general. So, this topic is very important, this stationary process, because especially WSS, because here we are bothered about only correlation and mean, and correlation become easier functions, mean becomes just a constant and correlation becomes a function of only one variable, that is lag variable. This has got tremendous application in filtering, communication, signal processing, control. Okay. So, in the next class we will continue from here, we will get into some kind of some examples of WSS processes, and a particular process which is very important in many communication examples for that matter. It is called cyclostationary processes. So, we will be considering them. Okay. Then we will consider linear systems, linear time invariant systems whose input is given by a random process which is WSS. What happens to the output? Okay. This kind of studies we will make afterwards. So, that is all for today. So, thank you very much. Okay. So, we start today important topic, that is cyclostationary processes. It is a special kind of random process which is not fully stationary, but it does exhibit some sort of stationarity and occurs frequently in many applications, especially in digital communications. Also called periodically stationary processes. Actually, these processes are such that their statistics that vary periodically over a constant time period. Okay. That is, if I talk of a cyclostationary process which is strict sense cyclostationary, that is, if x t is SS stands for strict sense cyclostationary, this would imply that if you take the probability distribution of f, that is, let me make it capital. By the way, what does this mean? Though we have already done it, but still there is nothing wrong in just restating what you already know. This is the joint probability distribution function of any random process x t. That is, it is the joint probability of, that is, by definition what is this? Probability of what? X at t1 lying less than equal to x1, x at t2 lying less than equal to x2 dot x at Tn lying less than equal to capital Xn. This is the joint probability. This is called the probability distribution. Okay, and this number n, there is a number of sampling points you are choosing, that is purely up to you. You can take it from 0 to up to infinity, because d theta n is minus d alpha. So, minus comes and the two integral limits are interchanged. So, minus sign goes, and this is your alpha plus tau comma alpha. From this again it is obvious, okay, because the entire thing is periodic over alpha over a period capital T. Still, if you are not convinced, you can break the integral into two halves. One is from 0 to t, that is 0 plus to t, same thing. Another is from t minus t to 0 minus, same thing, okay, dt. Concentrate on this integral. Second one, here again bring this variable alpha prime is alpha plus t, same way. So, d alpha and d alpha prime are same. When these integrals are with respect to alphas. D alpha so, d alpha and d alpha prime are same, and when alpha becomes t minus capital T, alpha prime becomes t. When alpha becomes 0, alpha prime becomes capital T, and the two integrals can be brought under the same one, and you get the result. That result, that is a function of tau alone. What you get is r, you can call it alpha, or you can bring back t again, say does not matter, because that is an integration variable t dt. So, you can call it alpha as well instead of t, 0 to t 1 by t. This is your r tau. So, this process is strictly in the stricture stationary. Okay. These are some applications in communication. We will take one example. Okay. The example of pulse amplitude modulation waveform PAM. So, that will give a practical feeling, and you will understand why we spend some time on it. After that, we will move to systems, that is processing of random processes by some linear systems or nonlinear systems, time invariant systems and all that, and that will take us to finally spectral analysis, power spectral density and things like that. Okay. So, that is all for today. Thank you very much.